Hi everyone. Today I'm going to explain two of the body's major bioenergetic pathways, the ATP phosphocreatine system, also known as the ATP-PCr system, and anaerobic glycolysis. Instead of simply defining these pathways, I'll use one exercise, a squat, to demonstrate how our muscles produce energy during different stages of a workout. This makes it easier to understand how these pathways work together during exercise. Let's start with a heavy squat. Imagine I'm about to perform 3 heavy repetitions. Instead, I unrack the bar, my muscles need energy immediately. The energy comes from ATP, or adenosine triphosphate, which is the body's energy currency. The problem is that our muscles only store a small amount of ATP, so to keep producing force, they quickly regenerate ATP using another stored molecule called phosphocreatine, or PCR. The reaction is simple. ADP plus phosphocreatine becomes ATP. Because both ATP and phosphocreatine are already stored inside the muscle cell, this system produces energy almost instantly. That's why it's perfect for explosive movements like heavy squats, deadlifts, Olympic lifts, or jumping. However, these stores are limited and generally provide enough energy for only about 10 to 15 seconds of maximal effort. These heavy reps are powered primarily by the ATP-PCr system because they require maximum force over a short period of time. So what happens if I don't stop after those first few reps? Well, let's say I reduce the weight and then continue the set for more repetitions. My muscles still need ATP, but my phosphocreatine stores are becoming depleted. Now another energy pathway begins contributing much more. This contributing pathway is called anaerobic glycolysis. Anaerobic simply means that this pathway does not require oxygen to rapidly produce ATP. Instead of using phosphocreatine, my muscles begin breaking down glucose that is stored as glycogen. During glycolysis, one glucose molecule is broken down into 2 pyruvate molecules. Although 4 ATP molecules are produced during the process, 2 ATP are used in the beginning, giving us a net gain of 2 ATP. Glycolysis also produces 2 NADH molecules, which carry high energy electrons. When exercise intensity is very high and oxygen delivery can't keep up, pyruvate is converted into lactate. And this is actually beneficial because converting pyruvate into lactate regenerates NAD. Without NAD, glycolysis would stop and ATP production would slow dramatically. So lactate actually helps glycolysis continue producing energy during intense exercise. Now I'm breathing harder. The bar is moving slower. My legs are starting to burn. This longer high-intensity portion of the set relies much more heavily on anaerobic glycolysis to continue producing ATP. An important concept to take away from this is that these pathways don't work independently. They actually overlap. During the first few seconds of my squat set, the ATP-PCr system provides most of the energy because it is the fastest way to regenerate ATP. As phosphocreatine stores begin to decrease, anaerobic glycolysis contributes more ATP to keep my muscles working. If I were to continue exercising for several more minutes, my aerobic energy system would gradually become the dominant source of ATP production. So rather than switching from one pathway to another, the body simply changes which pathway contributes the most depending on the intensity and duration of exercise. The ATP-PCr system provides immediate, explosive energy for about 10 to 15 seconds, making it ideal for a heavy, powerful movement like the first few repetitions of a squat. As exercise continues and phosphocreatine stores decrease, anaerobic glycolysis becomes more important by rapidly breaking down glucose to produce ATP without oxygen. This pathway produces a net of 2 ATP and forms lactate to regenerate NAD, allowing ATP production to continue during high-intensity exercise. Understanding these pathways helps explain how our muscles meet changing energy demands throughout a workout. Thank you for watching.